I'm here to say about graph representations using adjacency matrix and incidence matrix. Let us start through the video. Let us start with introduction to graph representations. Graph representations are crucial in understanding the structure and relationships within graphs. These provide comparative analysis. Uh, we discussed two types of representations in this video. One is using adjacency matrix and another is using incidence matrix. And we'll also discuss about the applications and advantages about the what is an adjacency matrix. Adjacency matrix is a square matrix which is used to represent a finite graph. The elements indicate whether pairs of vertices are adjacent or not in the graph. One indicates that the edge exists between two vertices, while 0 indicates there is no edge. This is efficient for dense graphs. What is an incidence matrix? Incidence matrix represents the relationship between vertices and edges in a graph. Rows correspond to vertices and columns correspond to edges, while entries indicating whether a vertex is incident to an edge. This representation is especially useful for bipartite graphs and those with multiple edges. Here we are going to see graph representation of undirected graph to adjacency matrix. Here we can see that there are three vertices, which is 1, 2 and 0, and uh, the right side we have adjacency matrix representation. Each element has mapped with another two elements in the graph. So 0 has an edge with 1 and 2, and 1 has an edge with 0 and 2, and 2 also has an edge with 0 and 1. So we'll map the edges as 1, 1 with the respective places. Now, if we come to directed graph, one is pointing towards 2 and one is also pointing towards 0, and 0 is not having any edge from its vertex to another vertex, so 0 doesn't have any values as 1 with 0 itself 1 and 2. As we see here, 1 is mapped with 2 and 0. So for 1, we'll indicate 1 and 0 with 1 and 1 and 2 with 1. 2 is mapped to 0, so we'll map 2 and 0 with 1 and others are left normally. So this is how we represent a directed and undirected graphs using adjacency matrix. Now we will go to incidence matrix. Here as we can see, we have 5 vertices A, B, C, D and E, and the rows are vertices and columns are edges as we discussed in the previous slide. Here we use 1, 0 and -1 to indicate the edges. If the edge is going from an element to another element, like the first element will be marked as +1, the second element which is receiving will have -1. Here as we see, if we take edge 1, it is starting from node or vertices A and reaching to vertex B. So A has +1 and corresponding to B, edge 1 has represented as -1. For each edge, if we take edge 2 starts from A, so A and H2 has marked as 1 and H2 goes to C. So H2 corresponding to C is marked as -1. If we go to H3, it starts from B. So H3 and D are marked as +1. When the edge goes to A, so H3 and A are marked as -1. Similarly, every edge is considered and marked in this form. The final result is here. So now, if we compare the efficiency, adjacency matrices are more suitable for dense graphs due to their constant time edge lookup. In contrast, incidence matrices may be more efficient for sparse graphs as they reduce the number of entries needed to represent edges. Applications of adjacency matrices. Adjacency matrices are widely used in algorithms for graph traversal, path finding, and network analysis. They facilitate operations like calculating the degree of a vertex and performing matrix operations to determine connectivity. Their compact form makes them preferable in many computational applications. Applications of incidence matrix. Incidence matrices find applications in network flow analysis, graph coloring, and combinational optimization. They are particularly useful in representing multigraphs and can simplify the analysis of complex relationships between vertices and edges in various fields. Limitations of the representation. Both adjacency matrix and incidence matrix have their own limitations. Adjacency matrices can consume significant memory for large sparse graphs, while incidence matrix may complicate edge-related calculations. Understanding these limitations is critical for selecting the appropriate representation for specific applications. We come to conclusion. Understanding adjacency and incidence matrices is vital for effectively analyzing graphs. Each representation has its strengths and weaknesses, making it important to select the appropriate one based on the graph's characteristics and the intended application. Knowledge of these matrices enhances graph analysis. Thank you.